Hello everyone. Let us summarize whatever we have learned so far. In the fundamental principles, we have learned that there are constitutive relationships, state variables, and material constants for any given phenomena to define. To define any given phenomenon, we need to understand and distinguish what are the state variables, constitutive relationships, material constants. The governing equations in the continuum physics are basic principles, represent fundamental physical laws which are independent of matter or independent of material. So they are same for any given material, any given phenomenon. So such as conservation of mass, conservation of momentum, conservation of energy, etc. The dependent variables in these governing equations are the state variables because they represent the state of the system. However, we require additional equations to solve a given problem or to mathematically solve a given phenomenon. Such additional equations which are constitution dependent are called constitutive relationships, or depend on the material dependent equations are called constitutive equations. Constitutive equations therefore are basically a relationship between two different state variables, such as a relationship between void ratio and effective stress, or a relationship between effective stress and shear stress. So the equation constants in these state variables are called material constants. So we require to understand the material constant dependency on other state variables also. So once we identify what are the different constitutive relationships for a given phenomenon and establish the relationships and identify the material constants, we can understand the phenomenon. So this is the flow chart for the phenomenon prediction is like this. So this is a physical phenomenon. Or observation. So from this, after observing the physical phenomenon, we frame governing equations. For example, we can think of a consolidation settlement. There is a slurry in a tailing ponds, the mine tailings would settle with time. So the phenomena here is settlement of mine tailings with time. So it's a consolidation settlement. So to predict that phenomenon, we need to develop governing equations. So such as we could utilize the basic physical laws like conservation of mass, conservation of momentum or force equilibrium, and energy conservation. So here consolidation settlement. So from these governing equations, we identify the state variables. Maybe the density or any other state variables we identify. So from that, so in this particular case, the state variables are maybe the void ratio is reducing because the volume is reducing. So the void ratio is decreasing with time. So therefore void ratio is one state variable. The stress state would differ with depth. Maybe the effective stress is varying with depth. So you have another state variable like sigma dash. And pore water pressure also changes with time. So therefore it could be another state variable. So once we identify, we can develop constitutive relationships that provide interdependency of different state variables. So, this could be a relation between void ratio and effective stress. So, this is void ratio versus sigma dash, or it could be the hydraulic conductivity also changes with depth. So, hydraulic conductivity is a material constant, but it could change with void ratio. So, you may require another relationship such as this. So, once we have the constitutive relationships, we identify the material constants. The material constants could be AV or MV, or could be your CC, etc. So, once we have this, again R could be CV also. So, these are the material constants. Once we identify these constants, now we can predict the phenomenon. The phenomenon is settlement versus time. If the phenomenon does not, then we compare this phenomenon with the physical phenomenon. If it does not match, there may be more constitutive relationships required. Therefore, so by providing those constitutive relationships, we try to match the prediction or try to get the good prediction of the phenomenon. So, for example, the one-dimensional consolidation given by Terzaghi, which uses only conservation of mass and which uses Darcy's law also, which combines these two, and it provides a governing equation which creates a governing equation. The state variables that it considers is pore water pressure, sigma dash and E. So, the constitutive relationships are void ratio versus sigma dash, which are assumed to be constant at any given change in the effective stress, and it uses a K versus E relationship. K is assumed to be constant for a given increment of the loading. K is assumed to be constant, and which derives the coefficient of consolidation. And from the phenomenon, we in fact predict the CV value, and we match the governing equations, or we match the developed model with the physical phenomena observation to determine the CV. This coefficient of consolidation is used in the field for estimation of consolidation settlements, the rate of consolidation settlements. Similarly, in unsaturated soils also, we need to identify what are different state variables so that we can develop governing equations and we can develop constitutive relationships for understanding the phenomena. In unsaturated soil mechanics, we have seen that we have three-phase system where we have water, air, water and solids. So, this is solids, and you have air and water. So, you have volume ratios generally considered on this side. So, the volume fractions are considered generally in this side: volume of air, volume of water and volume of solids, and this is mass of air, which is 0, and mass of water and mass of solids. So, the air phase generally defined as the pore space which is not occupied by water. So, that is called air phase, and water phase is the pore space which is not occupied by air. However, the air phase also contains water vapor, air phase contains water vapors, and the water phase contains dissolved air. As a solute, you have dissolved air, and the phases are no means pure. The water can exist in the air phase as water vapor, and air can exist in water as dissolved air. depending on different conditions like pressure, temperature, etc. So solids are generally the range of solids vary from very fine grained soils such as clays, silts and organic matter to coarse grained soils like sand and gravel. So the air phase, when you consider, the air phase has certain state variables such as density of air, which is an important state variable which governs the flow through unsaturated soils. So the density of air is estimated from this particular equation. Here UA is the air pressure, molar mass of air, R is gas constant, T is temperature. So the molar mass of a substance is the mass of substance divided by the amount of substance, which is expressed in kg per kilomole or gram per mole, and UA is atmospheric pressure, which is expressed in kilopascal. R is gas constant, which is 8.314 joule per Kelvin mole. Temperature is in Kelvin, and the density of air we have estimated at standard temperature of 25 degrees and 101.325 kilopascal pressure. This value is 1.185 kg per meter cube. The density of air is sensitive to the pressure and the temperatures. So the variation of density can be represented with a mathematical equation as this. So the density of air increases with increase in the air pressure, but decreases with increase in the temperature. As with the increase in the elevation from the mean sea level, the pressure decreases, the atmospheric pressure decreases, therefore the density of air decreases. This was explained simple illustration where if you fill a water bottle with air at higher elevation, close it with airtight and bring it to lower elevations or bring it down from the hillside, and when you bring it down, because the air pressure increases in the surroundings, this can crush the water bottle. This was explained during this discussion. This was explained earlier. So the temperature increases, the density decreases. This could be understood from sea breezes we see on the shores, because the land quickly gets heated up, but the air above the sea relatively is cooler compared to the air above the land. So therefore the air above the land density decreases, therefore it gets uplifted. This is filled, the space is filled by the air which is coming from the sea. So you get a cool breeze. So this is how the air circulates. Coming to the water, this is air. Coming to the water, if you look at the water density, water density has direct influence on the physical and mechanical behavior of unsaturated soils. The water density varies with temperature in this manner. As the temperature decreased, the volume of water decreases. So therefore the density increases and reaches one critical value, and beyond that the volume increases or density decreases. So this maximum density which is achieved, or lowest volume which is achieved, is at 4 degrees Celsius and which is 1000 kg per meter cube. This is around 996. Increase in the volume below 4 degrees is called anomalous expansion of water. Because of this, the ice floats on water. Ice which is lesser dense is less conductive to temperatures. Because of this, the aquatic life survives in the cold countries, because once the ice forms and it floats at the surface, ice is less denser compared to waters colder than this, compared to waters, because of this phenomenon, anomalous expansion, and when it floats it will act as a thermal insulation or partially thermal insulation, and it does not allow heat to transfer, so that beneath the ice the temperatures are maintained at higher values, because of which the aquatic life survives. If whole thing freezes continuously, then aquatic life cannot survive. Apart from dependency of water density on temperature, the water density significantly changes due to physico-chemical effects. We have seen that the clay particles are colloid. They are plate-like particles which has a negative charge on the surface due to isomorphous substitution, and therefore there are positive ions acquired from the environment during their formation or during chemical weathering process, and they are present at the surface. So now when the water is available, the water hydrates all these cations, and it also hydrates internal lattice and also external surface. When this water adsorbs, the water is available as a thin film around individual clay platelet. This water content can be as high as 15% at hydrate state for montmorillonite rich clays. This was explained earlier. So therefore, water as it got adsorbed on the surface of the clay, which is tightly held on the surface in an adsorbed form, the density of water is different from the free state. So if we can draw density of water or water density in gram per centimeter cube, and gravimetric water content on x axis, it is observed that the water density can increase to very high values. This may be 1.4 and this is 1. So as the water content decreases, when we are going in this direction, the water content decreases, the density of water increases, because the water which was held in the adsorbed state has very high densities. The densities can even reach to 1.8 gram per centimeter cube for montmorillonite rich clays. This was recent observations given by Liu in 2018. Other than the density of water and air, there is a viscosity of air and water. Viscosity of fluid is defined as the ability of fluid to deform under shear stresses. So the hydraulic conductivity of water and air depend on or get influenced by the viscosity of air and water respectively. The viscosity influences the hydraulic conductivity of both air and water. So therefore, the determination of viscosity of air and water are important. Dynamic viscosity, which is represented with mu, has units of Newton second per meter square or centipoise. This expresses the resistance to fluid flow. Another one is kinematic viscosity, which is expressed with nu, which is the ratio of dynamic viscosity to the density, which is used in analyzing the Reynolds number. So if we see the dynamic viscosity of water and air, dynamic viscosity, for the water the dynamic viscosity decreases, but for air viscosity increases, but for air the viscosity increases. So this is for water and this is for air. So this value at one particular temperature, this value is around 10 power minus 3 in Newton second per meter square, and at the same temperature this value may be very small. This is how the ranges are. So, mu of water at 20 degrees is 1.002 centipoise or 0.1 Newton second per meter square, and mu of air at the same temperature is 0.0018 Newton second per meter square. Air viscosity increases with temperature. As the temperature increases, the air molecules get additional energy and they collide each other, therefore the viscosity increases. On the other hand, the water viscosity decreases with increase in the temperature, because the increase in the temperature makes the water molecules to overcome the intermolecular forces. So, this decreases the dynamic viscosity of water. Understood the thermodynamic equilibrium between different phases. We have understood from a given beaker or taken one glass of water. For example, if we take a glass of water, so this is water. In this you have water molecules. These water molecules which are available at the surface would leave the surface and go to the air phase, because the intermolecular force at the surface is not strong enough to hold them back into the liquid. So, they go into the air phase. For example, if this is closed by a lid, the water molecules which go into the vapor or in the air phase would eventually have to come back by hitting this plate and again go into the water phase. After equilibrium, the number of molecules which are leaving from the water phase would be equal to the number of molecules which are coming into the water phase. So, at this equilibrium, for example, this is coming out and this is going up, this is leaving the surface. So, now the molecules which are actually coming to the water phase are called condensation, and molecules which are leaving the surface are called vaporizing. So, therefore, the number of molecules which are hitting the surroundings or surface, this plate, the pressure which is exerted by these molecules, these vapor molecules on the lid surface is called vapor pressure. Or the number of molecules which are available in this space also can be defined based on the density. So, number of vapor molecules or the mass of these molecules per unit volume can be defined as vapor density. So, this vapor density is nothing but the total humidity and relative humidity is defined based on the vapor pressures. So, based on the partial pressure of all gas components which are proportional to the molar fraction of each component, this is what we have defined. Ui by Ua is equal to N I by sigma Ni. So, the partial pressure of each component is related to the molar fraction of those components, or it could be expressed in terms of volume fractions also, because the ideal gas volume is known, that is 22.414 liter per mole. So, this vapor pressure increases with increase in the temperature, because when the temperature is increased, more energy is given to the molecules of water and they can overcome the intermolecular forces and then they try to escape from the surface. Therefore, more number of water molecules exist in the gas phase, therefore more pressure is exerted. So, therefore, the vapor pressure or vapor density increases with increase in the temperature. As we defined, the total humidity is total or absolute humidity. I am sorry, this is absolute. So, this is absolute. So, the absolute humidity is mass of water vapor in a given unit volume is called absolute humidity. On the other hand, the relative humidity RH is defined with respect to the partial pressure of vapor. So, this is the ratio of absolute humidity in equilibrium with some solution to the absolute humidity in equilibrium with pure water. Which is expressed in percentage. So, if you take a pure water and the density of vapor which is present on the above this water, pure water, which defines the absolute humidity, and if you take salt water or any other solution, the humidity or relative density above this salt solution and the ratio of these two, the absolute humidity above the salt solution in equilibrium and the ratio of absolute humidity of the vapors above the salt solution and the vapor density above the pure water, and this ratio is called relative humidity. So, this relative humidity decreases as the salt concentration increases, and it also depends on the type of salt which is present in a given solution, and also it depends on temperature. The saturated vapor pressure is defined to understand what are the general ranges of relative humidity, because even though you have pure water nearby, the relative humidity cannot be 100%. The relative humidity decreases due to the presence of some solute or presence of some salts in the solution, or due to these factors the relative humidity decreases. And to understand the variation in the relative humidity and formation of dew points, etc., we require the variation in saturated vapor pressures with temperature. So, this is vapor pressure and this is temperature. So, this is how the saturated vapor pressure varies. This increases exponentially nearly. So, the saturated vapor pressure, this can be expressed with an equation in terms of kilopascal. This is called Titton's equation, 0.611 times exponential of 17.27 T minus 273.2 divided by T minus 36. So, this is Titton's equation, and we have other equations also. I have discussed other equations also for fitting this saturated vapor pressure. Generally, either soil or in the atmosphere, the vapor pressure may be somewhere here. The temperature of the atmosphere is this much, and the vapor pressure is represented by point A here. Point A here. Now, we can reach this saturated vapor pressure in two ways. One, by decreasing the temperature. So, we follow this curve and we hit this one, we get the saturated vapor pressure. Or if you increase the vapor pressure by keeping the temperature same, and we also reach the saturated vapor pressure line. So more often we see that in the atmosphere, suddenly when the temperature drops from here to here, there is a formation of dew or condensation that takes place. Let us solve one simple problem to understand the dew formation, which is you have a soil sample. So in the atmosphere, currently the relative humidity is 80%. Relative humidity is 80% and the temperature is 22 degrees Celsius. And the question is, what is the dew point temperature when the vapor density remains constant? For the dew point to form or to hit this saturated vapor pressure line, what is the temperature required? So this information is sufficient to estimate dew point temperature. First we can estimate what is the saturated vapor pressure at this particular temperature. This temperature is 22 degrees Celsius and this is dew point temperature, which is not known. So we can estimate the saturated vapor pressure corresponding to point A, say this is B, saturated vapor pressure at A or at 22 degrees is equals to 0.611 exponential of 17.27 into multiplied by 22 divided by 259.2, which is equals to 2.64 kilopascal. So we estimated what is point C. At point C, the vapor pressure is 2.64 kilopascal. However, the relative humidity is known, which is 80%. Therefore, we can calculate UV at A. UV at A is 80% of 2.64, which is 2.11 kilopascal. So therefore, we know the vapor pressure at point A. If this is known, when the temperature is decreased, the vapor pressure remains same, but this vapor pressure, the vapor pressure at the dew point. So the saturated vapor pressure at point B and vapor pressure at A both are same because it maintains the same vapor pressure, but the temperature only decreases. So therefore, we can estimate, we can say that the vapor pressure at B, that is dew point, that is at saturated, is equals to vapor pressure at A. So we have the saturated vapor pressure where at the dew point, so that is 2.11, which can be equated to 0.611 exponential of 17.27 times. So this temperature is not known. So this is T plus 237.2 in terms of degrees Celsius if we write, and when we solve this, we can get T equals to finally 17.07 by say 0.928, this is equal to 18.4 degrees. So this is 22 and this is 18.4 degrees. If nearly a 4 degrees drop in temperature takes place, then dew forms. We see that the small droplets drop. So you can feel the water droplets. So this is a dew formation. And this concept is very, very important in future, understanding dew point potentiometer principle, which is developed for estimation of total suction of the soil, which is a important state variables for unsaturated soil mechanics. And in the dew point potentiometer, so the sample is taken, but the sample's initial humidity is not known, only temperature is known. Then when the sample is placed in this dew point potentiometer, temperature is reduced gradually so that they can find out, so that the dew point can be found out using some physics principle. Once the dew point is found or dew point temperature is found, the existing relative humidity can be found. This is an inverse analysis of this particular problem, same problem. So these concepts are very, very important for understanding the principles of several operators used for estimation of state variables of unsaturated soils. Thank you.